Alright guys, so in this section we're diving into chapter 2, and 2.1 starts it on off with an overview of quadratic functions. And we all know the quadratic function itself is just a polynomial function that does in fact have a degree of 2. So the goals within this section, we would use the characteristics of quadratic functions to sketch the graphs, analyze the graphs as well, write functions in standard form, and use quadratic functions in real life applications. So obviously we know what our standard form looks on like. We're dealing with ax squared plus bx plus c, where a, b, and c are real numbers. We know them as the leading coefficients of these particular terms for our quadratic function. Now, think to yourself, quadratic functions, what kind of graph do they produce? Hopefully remember that they do produce that parabolic graph. All right, so what are we going to start looking on into? We're going to start kind of reviewing some of the characteristics of a quadratic function. Now, remember specifically, those quadratic functions have an axis of symmetry, right? Because that vertex will create symmetry on both the left and the right-hand side, or the top and the bottom, depending on what the end behavior is of the graph, okay? And so we call that symmetrical line an axis of symmetry. Where we can find this axis of symmetry, as we just mentioned, can be found at the vertex itself. The x-coordinate of the vertex for a normal upward or downward facing parabola will be the equation for the axis of symmetry. The y-coordinate, if it is a horizontal facing parabola, will be your line or axis of symmetry for a horizontal facing parabola. Now the leading coefficient tells us, remember, if it opens upwards or downwards. Now the leading coefficient being positive, that means we're going to have a concave up structure. If we have a if facing down, that means it's concave down, and it is a negative leading coefficient, or a is negative in our quadratic function itself. All right. So let's start off some pretty basic as we kind of look on into them. So if you have your graphing calculator handy, by all means go ahead and to look at it. But what I want to kind of show here in just this basic example is think about what is happening in each of these different scenarios. As you're looking at these particular functions, what is the real only difference between said functions? And hopefully you're understanding that the only real difference is the change in that leading coefficient. So what does the change of the leading coefficient actually provide us? Well, let's take a look. What if we went ahead and just did a quick sketch of these graphs? And so what we're going to end up noticing is that, let's go ahead and do our first one here of x squared. And so that is our basic parabolic function here. And let's just kind of give it a very traditional look to it. Well, what happens, let's say if I change colors here and I wanted to make it 1/3 x squared. Well, that's going to be a little bit more so out here and a little bit more so out here. And what would change if I made the leading coefficient 2? Well, believe it or not, that's going to be a little bit more inside here and a little bit more inside here. So the point of this, guys, is to understand, and this is going to be our green function, this is going to be our blue function, and then of course our red is going to be our x squared. But again, the point is to understand what the leading coefficient is doing. The leading coefficient is changing the width of the parabola itself. So even though 1/3 is smaller than 2, it actually means that we are going to have a wider parabola because the values of y are not as rapidly increasing as they are like when the leading coefficient is 2. The leading coefficient is 2, the y values are all doubling every single time you put in a new x value in there. And so they are quickly gaining some momentum and getting up towards positive infinity faster than they would. All right. So let's take a look here at our standard form of a parabola. Now, we know what the standard form of the quadratic function looks like, the ax squared plus bx plus c. But the standard form in this essence is a way to clearly identify the vertex of the parabola. Let me say that one more time. We put it into standard form as a way to clearly identify what the vertex of the parabola is. And so here we can see that f of x equals the leading coefficient a times x minus h squared plus k, where h and k is the vertex, and of course, like we said before, the axis of symmetry is the line x equals h. So as we continue to kind of push forward and move along as we go through some of these, what are some ways that we can maybe utilize this a little bit more so? And so let's take a look. So example 2, all right, it says sketch the graph without graphing utility, and the goal is to put it into standard form itself. Now, how are we going to put this into standard form? Well, it depends. How much you remember from Algebra 2? In fact, how much you remember from Algebra 1? And we talk about this in Algebra 1 as well, too. Well, we can make a nice shift by doing what we call completing the square. And we can complete the square. And behind this box, I have what I call the complete the square cheat. All right. Now, I'm going to provide you, all right, both the regular way of completing the square and what's always going to happen once you do, in fact, complete the square. And that is what's happening behind here. So if I'm going from ax squared plus bx plus c to standard form, what you will see is that your d and e, or in this case, we also have talked about them as h and k, all right? Now, h and k in this case are going to be a simple, I guess, formula, if you want to think of that. D will always be b over 2a. And e is always going to be c minus b squared over 4a. Now, it's up to you. For some individuals, the whole process of completing the square may be a challenge. We don't maybe remember how to do it as well. And some of you guys just may be better with rote memorization. You might be able to remember simply that the d can always be found by doing this, and this e, or the k, the y coordinate, can always be done being found this. So I'm going to leave this on up to you. So this is what you have kind of as a complete the square little cheat sheet for you, but I'm also going to go ahead and put it into a perspective of how back in Algebra 1 we did learn how to complete the square. All right, so first and foremost, we have f of x equals 2x squared plus 8x plus 7. If you remember correctly, one of the first parts that you wanted to find out when you did not have a leading coefficient as 1 is you wanted to see if there was a common factor in those leading coefficients. And in this case, we do see there is a a common factor in that leading coefficient. So I'm going to go ahead and factor it on out and kind of group it in a different sense. All right. So now, from this example, all right, we now have a goal in which we want to go ahead and to complete this square. Make this into a trinomial that is something that I can go ahead and find almost a perfect square of. And that's what it means to complete the square. So if you remember correctly, how do we go about doing this? Well, right now we have x squared plus 4x. And what we want to do is we want to add b over 2 squared, all right? Because b over 2 squared is going to allow us to actually complete the square. So let me change colors so we can see what we're adding. So we are going to add, all right, b over 2. Well, here is my b. It was 4. 4 divided by 2 is 2, and square it is 4. So I'm going to add 4, but I can't just add 4 to it because it's not what was in it in the beginning. So I'm also going to subtract it. Well, what's the point? You're just going to cancel them all out. Technically, they do cancel it out because it holds the truth value to it. However, by regrouping, I still have the opportunity to complete the square. Check it out. So 2 times x squared plus 4x plus 4. If I distributed that negative 4 the 2 to the negative 4, this really, in the end, becomes a negative 8 plus 7. Now, what am I looking at? Well, as I continue to simplify, now I have x squared plus 4x plus 4. Hey, that is the same thing as saying 2 times x plus 2 squared. And then negative 8 plus 7 gives us our negative 1. All right, so now I have gone ahead and I have put it into standard form. And again, the goal of this is so I can easily identify what my actual vertex is going to be. And remember, inside the x function, it's the opposite of what you see. And then for the y coordinate, it's exactly what you see. So my HK, my vertex, can be found at negative 2 and negative 1. So 1, 2, 1, bring it on down here. It does have a somewhat of a steep shape to it, so I'm just going to do a quick sketch and we get the idea of where it is. But again, we can use complete the square. Now, if you want to go back, test yourself, see if my little cheat sheet does give you the same response. I promise it does. But again, if you are more interested in finding kind of that what is it going to look like in the end approach, try the cheat. If not, then go with the method that we went ahead and have done on in the past. All right, guys, so now that's going to wrap up this video. This is going to be your last example. Give this one a shot on your own. I have added a little bit of a twist on in there. I want you to also find what the x-intercepts are going to be for this particular parabola that we're dealing with as well, too. So give this one a shot, and we're on to the next one.